Hey everybody, today we're going to start looking at acceleration. Previously we've been looking at constant velocity, but acceleration is actually a changing velocity. Acceleration is defined as the rate of change of velocity or how velocity changes over time, which can mean speeding up or slowing down. But because velocity is a speed or rate of motion and a direction, acceleration is also defined as a changing direction. So it could be any of those three things: speeding up, slowing down, or changing direction. But in equation form, we're going to do the rate of change of velocity. So changing velocity is delta for change and v for velocity, delta v. And if it's a rate, that is the change of something over time. So acceleration, mathematically, is going to be defined as delta v over delta t, or a change in velocity over a change in time. And one of the best ways to evaluate acceleration is with velocity time graphs, which we've looked at just a wee bit last week. So a velocity time graph looks like this. Obviously, we've got velocity and time. But on a velocity time graph, the slope gets pretty interesting. The slope is rise over run, and on a velocity time graph, the rise is how much the v changes. So say we were going to take the slope of this first section. The rise part would be 1, 2, 3, 4, 5, 6 with the changing velocity. Changing velocity equals 6, so that's meters per second there. And then our time is the run, so 1, 2, 3, 4, 5, 6, 7, 8 squares, but each is worth a half, so it's 4. Change in time is 4 seconds. So your slope here you get is delta v over delta t, which is the same as acceleration. So the slope of a velocity time graph, in this first case here, the slope being 1.5 meters per second squared, that slope for a velocity time graph equals acceleration. But before we get into looking at the acceleration specifically with this velocity time graph, let's just look at what's happening with the velocity time graph. We're going to start at 0. The 0 here is talking about velocity. So if we got 0 velocity, we're stopped. But as time passes, the velocity starts getting larger and larger in the positive direction. So since velocity is positive, that means we're moving in the positive direction. And because it's increasing in magnitude, we are speeding up. So this first little section, speeding up and in the positive direction. The second section, flat line, is a little bit weird. Previously, looking at position time graphs, the flat line meant we were staying still, but that's because we weren't changing position. Now the thing that we're not changing is velocity. So if we're not changing velocity, that's going to mean we have a constant velocity, but we're still moving because the velocity isn't 0, it's 6 meters per second. So our constant velocity there is positive 6 meters per second. We're still moving, just not speeding up or slowing down. Then we get to this middle section. This middle section is particularly interesting. So we start at 6 meters per second, and then we go towards 0. So what's happening is our number's getting smaller and smaller, but we're still on the positive side of the graph. So as the number gets smaller and smaller, we're slowing down, going from 6 to 5 to 4 to 3 to 2 to 1, all the way to 0 meters per second on this little stretch. So that part is slowing down. But then after 0, we keep going down and we go to the negative direction. So now we're at -1, then we go to -2, all the way to -8. So what we've done on this part down here is we've gone from 0 meters per second to 8 meters per second. But we're going in the negative direction now. So this first part, that was slowing down. Right when it hit 0, that was a stop. And this last leg right there, we're speeding up, but in the negative direction. So we slowed down, stopped, turned around, and started speeding up in the negative direction. Then we get to another flat line. This flat line means constant velocity again. Constant velocity. Constant velocity, and that constant velocity is negative 8 meters per second. So we're moving in the negative direction now. Negative 8 meters per second. And then this last little piece goes from negative 8 to 0. So we are slowing down all the way to a stop, but still moving in the negative direction. So to summarize again with this graph, I'm actually going to trace it in a different color so we can still kind of see the color. We started at 0 meters per second. We moved in the positive direction, speeding up. Then we stayed at 6 meters per second in the positive direction, held a constant velocity, still moving. Then we slowed down all the way to 0 meters per second, turned around and started speeding up again, but in the backwards direction, in the negative direction, till we went 8 meters per second in the negative direction, stayed at that velocity for a few seconds, and then we slowed down while still moving in the negative direction all the way to a stop. And while we were doing this, we were accelerating. We were slowing down or speeding up, which is called acceleration. And those accelerations could be calculated by finding the slope. For example, this first section right here, we said the rise over run is 1.5 meters per second squared. So that's the slope. At this part, where it's a flat line, your rise is 0, so your slope is 0. Flat line means slope of 0. So your acceleration was 0, which makes sense because you're going at a constant velocity. Your velocity is not changing. And you could similarly calculate the slope at the other two, well, at any of the other points, you've got another constant velocity here. But on your two other lines, you could calculate the slope to calculate the acceleration. Now, if we wanted to look at this on a velocity time graph, it's going to be a little bit difficult because to actually graph it really well, you kind of need a little bit of calculus knowledge or some knowledge that we don't have at this point. But we are going to show that the first leg is speeding up. So we're going to start off with a baby slope and get to a larger slope. See how it goes from flat to steep. That's speeding up. Then it goes constant velocity. That constant velocity is just a straight line. Sorry, my line looks a little bit weird. Then we slow down until we turn around. So then we're going to curve off, slowing down until we turn around and start going in the negative direction. And we're going to speed up in the negative direction so we can get nice and steep. And then hold that constant velocity for a little bit. And then we've got to slow down all the way to a stop. So there's going to be our velocity, or not our velocity, our position time graph. And that's pretty complicated. We're going to be looking at that a lot more in depth on Friday, so don't worry if you don't understand the position time graph for the acceleration. Just showing you kind of what it looks like as a precursor. We will get to that on Friday. All right, now that we've looked at acceleration on a velocity time graph, we need to know a little bit more about acceleration numerically according to the equation. Our question here says, what is the acceleration of a car if it goes from a rest to 27 meters per second in 2.8 seconds? Assume the car is moving in a positive direction. And we're going to start with a picture. Our position time graph looks like this: position and time. We know that it is starting at rest, so it's starting off really slow, well, stopped entirely, and it speeds up. So we're going to start a graph off slow and speed up. And a velocity time graph that starts off slow and speeds up looks just like a straight line. Start off with a low velocity or a zero velocity and get. So that's our image. Now we got to look at the givens. Our givens are that it starts from rest, and what rest means is a velocity of 0. Rest means velocity of 0 to 27 meters per second in 2.8 seconds. It's asking for the acceleration. Now we've got our equation, acceleration equals delta v over delta t. Now we're going to actually expand this a little bit. So our change in velocity, we're going to define as our final velocity minus the initial velocity. That's how much is the velocity changes, is the final minus the initial. And that's a little f for final, a little I for initial, over delta t. So in our question, we have that it starts at rest. That is velocity initial. Wherever or whatever velocity it starts at, that's the velocity initial. So that's 0 meters per second for this question. And then it goes to 27 meters per second. That's its final velocity. That's how fast it gets up to. From 0 to 27, and it takes 2.8 seconds. So delta t equals 2.8 seconds. And it says, assume the car is moving in a positive direction, so that means both of our velocities are positive, though you can't really have a positive, it's 0. We already have the equation written, and we're looking for acceleration. So it's solved for the correct variable, solved for A. Now all we got to do is substitute. For substitution, we get A equals delta V, or VF minus VI. VF is 27 meters per second. VI is 0 meters per second. And we're going to divide that by delta t, or 2.8 seconds. And if you do your math out for that, you'll get 9.64. And the unit on that is meters per second divided by seconds, which is just meters per second squared. That's your solution. The acceleration is 9.64 meters per second squared. All right, so just like yesterday, we can have lots of different questions asked about this one equation, solving for different variables. So we might have to rearrange that equation to solve for something else. And we're going to look at how to do that down here. The equation we start with every time is acceleration equals VF minus VI over delta t. Every time, that's what we start with. On this first section, we're going to solve for VF. Now, VF is right here. That's VF. So VF has two variables on its same side. It's got delta t and it's got VI. But according to order of operations, the first thing that we're going to have to do is get rid of that delta t that's in the bottom. Just going to multiply by delta t. And what you do to one side, you have to do to the other. So we're going to end up with delta t times A equals VF minus VI, because those delta t's will cancel. Delta t times A equals VF minus VI. And now it's really easy. All we've got to do is get rid of VI. It's being subtracted, so we'll just add it back in to make it go away on that side. What you do to one side, you have to do to the other. So you get VI plus delta t times A equals VF. And most of the time we won't write it exactly like that. You'll see it as VF equals VI plus A delta t. That's the equation solved for VF. VI is pretty similar. In order to solve for VI, which is here, in order to solve for VI, you have to get t out of the bottom again. So to get t out of the bottom again, you have to multiply by it. And you'll end up with delta t times a equals VF minus VI, same as last time. But now, instead of wanting VF, we want VI. But VI is negative over here, so what I'm going to do is add it to each side, because I like to do that. You get VI plus TA, or not TA, delta t times A equals VF. And to solve for VI on the side, then we have to subtract T, or delta T times A from both sides. So you get VF minus delta T times A, which is more commonly written as VI equals VF minus A delta T. And that's it solved for VI. And our last thing is solving for delta T. Solving for delta T is a little bit more difficult because it's in the bottom. So anytime a variable that you're solving for is in the bottom, you have to get it out of there. Have to get rid of it from the bottom and put it on the top somewhere. And we do that by multiplying by delta T on both sides. So those cross out and you get a delta T equals VF minus VI. To solve that for delta T, you've got to divide by A on each side. And you get delta T equals VF minus VI over A. Oh, sorry, that was a bad box. Need to redraw it. There we go. So those are the three algebraic solutions for VF, VI, and delta T. On your practice, you will be solving questions for each of these variables. If you forget how to do the algebra, come back here and check it out. But otherwise, get cracking on your practice. Let me know if you have any questions.